So now we are going to discuss about a numerical problem on the spectral hemispherical emissivity. So you can see it here. This is example 12.5. We are given with a diffuse surface at 1600 Kelvin and its spectral hemispherical emissivity is shown in the following figure. So you can see it here. This is the spectral hemispherical emissivity, means it is not dependent upon any direction. That is why it is written here the hemispherical emissivity. So from 0 value of lambda to 2 microns, the value is epsilon 1, which is actually 0.4. From 2 to 5 microns, the value of emissivity is 0.8. And from 5 to, let us say, infinity, the value is actually equal to 0. So emissivity in the range of 5 to infinite range of wavelength is 0. So we have been asked to calculate the total hemispherical emissivity and the total emissive power. So it's quite easy. We have to basically average out the value of the epsilon lambda epsilon. So what we will do in this particular case is we are known is the surface is a diffuse surface at 1600 Kelvin. We have to find the total hemispherical emissivity, total emissive power, and surface is a diffuse emitter. So when we say surface is a diffuse emitter, so we know that it is not dependent upon the direction actually. So we know that the total hemispherical emissivity is given by the equation 12.36. It is nothing but this equation. This is equation 12.36, where emissivity is given by epsilon lambda, E lambda b, D lambda, and this value is integrated over the total wavelength range from 0 to infinity. So this will give us the emission from a real surface actually. Okay, because you know that E lambda by EB lambda is actually equal to epsilon lambda. Okay, so this is the value. So if I have to calculate the value of E lambda, that would be equal to epsilon lambda into EB lambda. And when we will integrate it over the total range of the wavelength, we are able to get the value of the emissivity with the condition that we divided by EB actually. So as we have already told that epsilon is not a function of direction, so we can integrate it by parts actually. First of all, we can take the range of lambda from 0 to 2 with epsilon 1 taking outside the integration sign because the value is constant for this particular range, and inside the integral we have E lambda b D lambda divided by EB. Similarly, epsilon 2 is also constant between the wavelength range from 2 to 5 micron meter, and inside it is E lambda b D lambda divided by EB. So it's quite easy. If you see this expression here, it is nothing but the fraction of energy lying between 0 to 2 microns and 0 to 5 micron. So that is how we can calculate this value. And similarly here also it is the fraction of the energy lying between 0 microns of wavelength to 2 microns of wavelength. So that is why you can see it once again. This is the same equation which I have written in the last page. So here you can see epsilon is equal to epsilon 1, fraction of energy between 0 to 2 micrometer, and epsilon 2, fraction of energy between 0 to 5 microns, and minus fraction of energy between 0 to 2 microns. So that is how we can calculate this value. And we know the value of lambda 1 T. Lambda 1 is 2 microns. Temperature of the body is given as 1600 Kelvin. So lambda T is 3200 micron meter Kelvin. So I have particularly kept this value, which is 0.318. So it is written here. This is the fraction of the energy. Similarly, lambda 2T, it is actually equal to 5 microns into 16,000. So it would be 8,000 micron meter Kelvin, and the value corresponding to this value is 8,000 micron meter Kelvin. It is 0.856. So it is written here. So it's quite easy. Now we can calculate the value of the epsilon, which is the total hemispherical emissivity. So it's 0.4, which is this particular value, or this particular value multiplied by this value 0.318, then plus 0.8, which is this particular value of epsilon 2, and 0.856, which is the fraction of energy lying between 0 to 5 microns, minus 0.318. So the total value comes out to be 0.558. Now, once I have calculated this value, to calculate the value of total emission, emissive power, that would be equal to epsilon times EB. So epsilon sigma T4, that is the value of EB actually. So 0.558 is the total value of the emissivity, and multiplied by 5.67 into 10 raised to the power minus 8 watt per meter square Kelvin raised to the power 4. This is the value of sigma, which is nothing but Stephen Boltzmann constant, multiplied by 1600 Kelvin raised to the power 4, and the answer comes out to be 207 kilowatt per meter square. Now let us proceed to the next topic. This we have studied earlier also, but I am repeating it here with some modification. So once again, absorption, reflection, and transmission by the real surfaces. Okay. So we know that spectral irradiation G lambda, which is having a unit watt per meter square micron meter as the rate at which the radiation of the wavelength lambda is incident on a surface per unit area of the surface and per unit wavelength interval d lambda about lambda. So you can see it here. This is the irradiation which is falling here on the surface. It's denoted as G lambda. So out of G lambda, some part of this lambda will be G lambda will be absorbed, some will be reflected, and some will be transmitted. So everything is shown here. This is the transmitted part, and we are considering it as a semi-transparent medium. This is the absorbed part here, and this is the reflected part here. So it may be this irradiation may be incident from all possible directions and may originate from several different sources. The total radiation G. So if I have to calculate the total irradiation, that means I have to cover the whole wavelength range. So that becomes G. So its unit would be watt per meter square, and it involves all spectral contributions. Here we consider the processes resulting from the interception of this radiation by a solid or liquid medium. So liquid medium will be a sort of semi-transparent medium, whereas the solid medium will be a opaque medium through which the light cannot, through which the energy cannot be transmitted. So in most general situations, the irradiation interacts with a semi-transparent medium such as a layer of water or a glass plate. So that has been shown here in this particular diagram. For a spectral component of the irradiation, portions of this radiation may be reflected, absorbed, or transmitted. So this is the equation we have discussed about it earlier also. This is the total irradiation in the range of total irradiation falling on the surface, and it is the spectral irradiation basically. So a part of it is reflected, a part of it is absorbed, and part of it is transmitted. So total will be equal to G lambda. So in most of the engineering applications, the medium is opaque to the incident radiation, that is transmission is not existing. The remaining absorption and reflection processes may be treated as a surface phenomena. Okay, so we are talking about only surface. No, it's not a volume phenomena. That is, they are controlled by the processes occurring within a fraction of a micrometer from the irradiated surface. So it's very small thickness of the opaque surface is there through which in which the absorption and the reflection takes place. It is therefore appropriate to speak of irradiation being absorbed and reflected by the surface with the relative magnitudes of G absorption and G reflection depending on and the nature of the surface material. Now let us talk about the absorptivity. Absorptivity is a property that determines the fraction of the irradiation absorbed by a surface, and it may be characterized by both directional and spectral dependence. So that means it have both directional and spectral dependence. So first of all, we are going to discuss about the spectral directional absorptivity denoted by alpha lambda theta. Means it is dependent upon wavelength, the direction theta and direction phi of a surface is defined as the fraction of the spectral intensity of the radiation incident in the direction theta and phi that is absorbed by the surface. So here we are talking about the spectral intensity of the incident radiation. So alpha lambda theta will be given by I lambda incident, which is absorbed, and it is dependent upon lambda theta and phi divided by I lambda incident, which is dependent upon lambda theta and phi. Now just try to understand the difference between the two. This is the total rather spectral intensity of the incident radiation, whereas this one is the absorbed part of the incident spectral intensity of the radiation. So the ratio of these two is known as the alpha lambda theta. In this expression, we have neglected any dependence of the absorptivity on the surface temperature. So surface temperature is not involved here. Such a dependence is small for most spectral radiative properties. Now, let us talk about the spectral hemispherical absorptivity. When I say hemispherical absorptivity, so I am not considering any direction particularly. Spectral means over the wavelength range. So for most engineering calculations, it is desirable to work with the surface properties that are representing the directional averages. So we are not worried about the direction, and we are worried about the spectral value of the absorptivity. So spectral value of the absorptivity, also called as spectral hemispherical absorptivity, alpha lambda, is defined as G lambda absorbed. So total incident energy or total irradiation value which is absorbed, which is falling in a particular range of the wavelength, divided by the incident energy which is falling. So this is the absorbed part of the incident energy which is falling on the surface, and this is the total energy which is falling on the surface. So alpha lambda can be given as, now if we have to calculate the value of this G lambda absorbed, so how to calculate that value? See, we know that this is the incident energy which is falling in the direction lambda, in the wavelength range lambda, about this particular direction, multiplied by cos theta, sin theta, d theta, d phi. So if whenever you will see this, these four terms mostly come with all the values of incident or means spectral radiation, whether it is incident emission or something else. And then this is the incident radiation, spectral radiation, and here we are multiplying it by the alpha lambda theta, which is dependent on lambda theta and phi. So that will give me the total energy absorbed. Basically, if I integrate this total value, if I integrate this total value for theta varying between 0 to pi by 2 and phi varying between 0 to pi 2 pi, and divided by the total incident energy falling in this direction, okay, falling in this direction. So the ratio of the two will give me the value of alpha lambda. So I have not integrated it for the total wavelength range. That is why this value is for a particular wavelength range. Hence, alpha lambda depends upon the directional distribution of the incident radiation as well as on the wavelength of the radiation and the nature of the absorbing surface. So once again, same equation is written here. Now, suppose this surface is incident radiation is diffusely distributed. Diffusely distributed means I lambda I is not dependent upon this theta and phi. Diffuse always means the the dependence on the direction is neglected actually. So it is equal to I lambda E, which is depending upon only the wavelength value, and alpha lambda theta is therefore independent of phi. So the above equation will reduce to, so you can see it here. I have taken this value of I lambda I out of the integration sign here, and inside we are left with alpha lambda theta. And as I told you, alpha lambda theta is independent of phi, because we are considering that the total energy is falling in the whole hemisphere from 0 to 2 pi actually, okay, in the azimuthal angle range from 0 to 2 pi on the surface. So it is independent of phi. So what we can do is this d phi can be integrated over this particular range from 0 to 2 pi actually. So cos theta, sin theta, d theta. So in the denominator also I lambda I has been taken out, and this is the value in the denominator. So alpha lambda theta cos theta d theta d phi. So this is the value because this I lambda I and I lambda I cancels out. So then we can integrate this equation. This integration is quite simple, and finally you can also go through it. I am not going through it. So this is the value of the alpha lambda, which is twice the value of alpha lambda theta cos theta sin theta d theta, with the value of theta varying between 0 to pi by 2, and there is a 2 here also. So that is how we can calculate the value of alpha lambda. Now we can also calculate the value of total hemispherical absorptivity alpha. So total hemispherical absorptivity alpha represents an integrated average over both direction and the wavelength. It is defined as the fraction of the total irradiation absorbed by a surface. So this is the absorbed part of the energy which is falling out of this energy on the surface. So the ratio of these two will be known as alpha. So this is the average value. And if I have been given with the value of G lambda, what I can do is I can calculate the value of G absorbed. So this value in totality, if you see it here, this total value is the value of G lambda absorbed, okay, multiplied by D lambda, and integrating it from 0 to infinity will give me the value of total energy absorbed, divided by this is the total energy falling on the range from 0 to infinity. So that is how we can calculate the value of alpha. Alpha depends on the spectral distribution of the incident radiation as well as on its directional distribution and the nature of the absorbing surface. So this we have discussed earlier also. Now some important points about alpha and epsilon. Note that alpha is approximately independent of the surface temperature. So alpha is independent of surface temperature. The same may not be true for total hemispherical emissivity. So emissivity is a function of temperature, whereas alpha is not a function of temperature. Because alpha depends upon the spectral distribution, means the value of lambda of irradiation as well as value for the surface exposed to the solar radiation may differ appreciable from its value for the same surface exposed to the longer wavelength radiation originating from the source of a lower temperature. Okay, so uh, let us go further. I hope this is clear to you. Since spectral distribution Since spectral distribution of solar radiation is nearly proportional to the emission from a black body at 5800 Kelvin, it follows from the equation 12.44 that the total absorptivity to the solar radiation alpha S may be approximated as. So alpha S, or the alpha of the solar radiation, will be given by alpha lambda EB lambda corresponding to the value of temperature 5800 D lambda. So this is the energy absorbed from the solar radiation corresponding to 5800, and this is the total energy which is falling means solar radiation which is falling for the total value of the lambda varying between 0 to infinity. So that will be known as the solar absorptivity. The integrals appearing in this equation may be evaluated by using the black body functions as given in the table 0 to lambda. This we have already been calculating, and alpha, as you know, this is the equation 12.44, which is written here to make you understand that what is the equation 12.44, and based on that only we have defined this particular equation, which is related to the absorptivity corresponding to the solar radiation, basically nothing else. Now let us discuss about the reflectivity. The reflectivity is a property that determines the fraction of the incident radiation reflected by a surface. Now let us discuss about the spectral directional reflectivity, that is rho lambda theta of a surface is defined as the fraction of the spectral intensity incident in the direction theta and phi which may be reflected by the surface. Hence rho lambda theta, which is a function of lambda theta and phi, is equal to incident energy which is actually reflected, and this incident energy is of a particular wavelength in a particular direction theta phi, divided by the total energy which is falling in this particular wavelength range in this particular direction theta and phi. So this is the energy which is spectral intensity of the radiation which is incident on the surface, and this is the reflected part of this incident radiation. And if we want to calculate the spectral hemispherical reflectivity rho lambda, then it is defined as a fraction of the spectral irradiation that is reflected by the surface. So it is G lambda reflected divided by G lambda total falling on the surface, and it is rho lambda. So it is dependent upon the wavelength only. And once again we can we have written once again the same thing, same value. It is written here. If you can see it, previously also we have written the same value. And now we have written it in terms of rho lambda theta actually. So rho lambda theta multiplied by I lambda I, which is actually, when we multiply both these terms, this basically becomes the absorbed value in this direction actually. Okay, so this is varying between 0 to 2 pi, which is the value of integration of for phi, and this is for the theta. Okay, divided by, this is the total energy falling in this direction actually of theta and phi. And if we want to calculate total hemispherical reflectivity, then total hemispherical reflectivity rho is defined as G reflected divided by G. What is G? G is the irradiation which is reflected, and G here is the total incident energy falling on the surface. So the ratio of the two is rho actually. This is the reflected part and this is the total energy which is falling actually. So once again, total reflectivity is G reflected divided by G, and in which case rho can also be calculated as rho lambda, G lambda, D lambda divided by G lambda, D lambda, and both are integrated over the range 0 to infinity. Surfaces may be idealized as diffuse, specular according to the manner in which they reflect the radiation. So you can see here it is the incident radiation and it is going in uniform reflected radiation of the uniform intensity. So it's a sort of diffuse surface. And if you see this, this is the incident radiation. It is falling at an angle of theta 1, and it is the reflected ray. It is going at an angle theta 2, but we are saying that theta 1 is equal to theta 2. So it means it's a specular reflection, means the energy is coming at a particular angle and also leaving at a same angle. So angle of incidence is equal to angle of reflection here. Now, what are the various types of the reflections? We have already discussed about it. Diffuse reflection occurs regardless of the direction of the incident radiation. The intensity of the reflected radiation is independent of the reflection angle. In contrast, if all the reflection in the direction theta 2, which equals to the incident angle theta 1, specular reflection is said to occur. This we have already talked. Although no surface is perfectly diffuse or specular, the latter condition is more closely approximated by polished mirror-like surfaces and the former condition by the rough surfaces. The assumption of the diffuse radiation is reasonable for most engineering applications. So now we talk about the spectral transmissivity. Spectral transmissivity is given by G lambda transmitted divided by G lambda, which is falling on the surface, and this is the total hemispherical transmissivity, which is G, or the irradiation transmitted divided by the radiations which are falling on the surface. And the total transmissivity tau can be related to the component tau lambda by the equation 12.53, which is G lambda transmitted multiplied by D lambda, and this value of G lambda transmitted is equal to tau lambda, G lambda, D lambda, and integrated over the whole wavelength range. And this is the total incident energy falling on the surface, which is given by G lambda, D lambda. And what are the spectral consideration? We know this value already. Rho lambda plus alpha lambda plus tau lambda is equal to 1. It is for the semi-transparent medium. For the properties that are averaged over the entire spectrum, it follows that, means we are calculating for the whole wavelength range, then rho plus alpha plus tau will be equal to 1. Of course, if the medium is opaque, that means tau is equal to 0. Tau is equal to 0, and the absorption, the reflection of the surface possessed for which alpha lambda plus rho lambda is equal to 1 and alpha plus rho is equal to 1. So opaque surface is 1 for which the transmission is 0. Now let us discuss about this numerical problem. I think we can do it in the next class. So I will end my lecture here.